Hi, this is the second video about a program that I wrote, DHO-REMOTE. And the program does an impulse response Bode diagram of a dot. So this time I would like to show you how you can measure a crystal. So I started up KiCad and I draw the setup instead of showing it on the picture. There is a stimulus. You need to have a generator. It doesn't really matter how much, as long as it can create square wave signal. The source of my generator is 50 ohm. That's also not that important. What is important is that the crystal itself should be in series with the scope input. This is channel 2, this is channel 1. And because my scope has 1 mega ohm impedance, I externally terminate with 50 ohm. So the generator sees a large 1 volt peak signal, a square wave signal on here. And it sees something here, and I want to know the transfer. So I want to know when it resonates. So this is my setup. I start a program. This program is called DHO-REMOTE. So you started with Python DHO-REMOTE.py. An argument needs to be given to the network address of the scope. In my case, that's, well, you can see it. That's not that interesting, but... So the first time that I started up, well, basically, yeah, let's show what there is on my screen. So I have a square wave signal on channel 1. Ooh. There's nothing special with that, and channel 2 seems to have nothing on there. So this is channel 2, this is channel 1. So channel 1 has a square wave signal, and I put it on 500 millivolt, and it is just barely hitting the maximum output. So that's what I want. Let's start with the normal setting. So if you increase the time base, then you can see that there is something on channel 2. It's regular level here. So you see that there is this is the response of channel 2. So I can give an FFT of channel 1. So it basically shows a decaying spectrum, a square wave on the input. And on channel 2, that's that tiny peak there. Basically you see a flat spectrum. That's because it is capacitive coupling. You see something here. And remind this, I'm testing a crystal, and I do not know yet what it is. Although if you look here, then you can already see that there is something special going on around this frequency. So these are just 2 FFTs of the 2 channels. You can just see what they are. And the next thing that I'll do is I'll just do a Bode plot. Then I'll press the button. So this shows the signal again. So basically the same as here, except that it is on the same scale. And my second channel is 10 millivolt per division, where my first channel is 500 millivolt division, because this signal coming out of the crystal is rather small. So I have a low volt per division here. And here it is plotted over each. So if you zoom in here, you can actually see that there is, well, let's zoom in. You can zoom with this button. If you look here carefully, then you can see, yeah, there's something going on there. Yep, that's the same as here, except on the same graph. Now here you see on the second, the middle chart, you see the frequency response, the FFT response of the channel 1 and channel 2. This is channel 1. And this is channel 2. So it's almost constant. And here you see the part that is interesting. Now if I zoom in here, then you can already see around 4 megahertz. That, well, if you know a bit about how a crystal works, then you can see that the amplitude response is sort of, it goes in series resonance, and it goes in parallel resonance. And by the way, the scale, the frequency scale is in logarithmic frequency. If you press the capital L key, which I will do now, then it becomes linear. So I will be doing that from now on more often. So I know already that my frequency of interest is around 4 megahertz. I could also have read on the crystal, and it also says 4 megahertz, so that's correct. In the third plot, you see the Bode plot. And the Bode plots, well, what you see here is that it actually starts to resonate here at, well, 20, 30 kilohertz, and then it gradually increases. In the scale here is minus 110 dBV up until minus 60 dBV. So this is basically a capacitor. And there is nothing interesting actually here, because we know already that at 4 megahertz, the interesting thing starts. And actually, it stops here at 1 megahertz, and there is a reason for that. Is the program has sort of a limit because of noise of 60 dB, and it doesn't display anything above it. So I can increase that to 100 dB and plot again. So now I see the same again, but it extends a bit further. And now you can see a bit more here. I'll zoom in this one. So this, if I keep the X key pressed, then I only do the X region. So that's what I want. So I just zoom in around here. And there you are. This is so the L key gives you the clear view. So around this frequency there is some resonance. Now one other tip is, so the triggering is done on channel 1 if everything is correct. So it should be, yeah, it's not entirely stable as you can see. That's probably the quality of the scope. What I can still do is average out the signal. Once I do that, it becomes a lot less noisy. And that's interesting for making the next plot. So you can sort of compare the noise. And what, yeah, let me also show, basically I'm only interested in in the region over there. So what I'll do is 3.95 megahertz is lower frequency and 4.05 megahertz is the higher frequency. I do exactly the same, except I display only the frequency of interest in this range. The only thing that I still need to do is, I prefer to do that, is the capital L, so giving a linear X scale. And now you can see clearly that what the transfer is. And the resolution is actually not determined by my generator. The resolution is 100 hertz. Of the frequency that I apply is a square wave signal is 100 hertz. But my memory depth and my sample rate are such that I only capture this region. So it is 0.8 millisecond to 0.8 millisecond. And if you calculate the frequency of that, so that's 1 over 0.8 millisecond, no, in millisecond times 2. So that's only 625 hertz. So this is the lowest frequency here, 625 hertz, is limited by the capture depth of the scope. But the advantage is that the frequency spectrum is very nice, because you only have one edge, and the frequency on the screen, which is where the FFT is taken from, is exactly in the middle of all the bins. So there is no ripple. I can also show that if I lower the time base. Once I do that, so now there is still 620 megasamples per second, but once I lower the time base to, well, I really need to lower it a lot because of the memory depth. So now at 200 microseconds per division, the sample rate drops to 312. And I can do that a bit further. Let's take 1 millisecond. So it's now 62 mega. And I do a Bode plot again. I still display the same region here, by the way. So what you now see is that here there was a square wave, but now the square wave is limited by my generator. So now I see the edges of the generator. And what the FFT does, it just says, well, at the end of this interval, it just repeats again and it goes over there. So you get a discontinuity at the end of the entire sample that has been taken. And the end sort of matches the beginning. So there's an artificial edge. And to prevent that from spoiling the result, there is a window taken over, a Kaiser window. So only this part is sort of taken. But what happens still is that because that window is not perfect, you see a little bit. I'll zoom in this one. So I only do the X expansion. So basically you see some noise. It is not a lot, but it is sort of 1 or 2 dB noise. And that's similar to what you see in this result. So actually this one is cleaner because the time, there is only one edge captured and the falling edge is not captured. So the FFT is very clean, and I think the resolution for measuring this crystal is yeah, I think it is very good. So I can put it full screen. Zoom button. Let's zoom out a bit. That can be done with the right key. Now let's zoom in again. Now perhaps this is a bit too much. But what you can clearly see is that yeah, let's zoom in a little bit. By the way, this is pie plot. So now you see 5 kilohertz per division, and all those crosses are actually measurement points. So here, so this is actually the real resolution of the trace. I didn't do that for the amplitude. So the amplitude curve is a smooth curve, and there is here some. Yeah, you see that this is a discontinuity. That means the resolution of these points is a bit too coarse. This point, if it would be just a bit on the right, on the left, then it might be lower. So this is now minus 65 dB. And that could be improved by lowering the time base a bit further. But at least you can see that this method of using of creating a Bode diagram from a square wave signal is actually quite usable. Later on, I will show other examples with well, with an RC network or an LRC tank, for instance.